Hi everyone, it's Vicky here, and in this tutorial we're looking at this cool underwater bubble effect. It's a simple setup, however we are using several lines of Vex, but even if you skip those parts you'll still get a decent result. I'm using Houdini version 19.5, but you can get the same result in any Houdini version above version 17. But before we start, let's find some references. So here I gathered several images just to help me understand how the bubbles behave, how they move underwater, how fast they come to the surface, and how they split up. And it's always very useful to have those references on maybe the second screen when you work on your simulations. Let's start by setting our frame range in Houdini. So I like to start my frame range on 1001, and this is because if I need to add any frames before that, if I need any pre-roll, let's say 100 frames, then I can easily do this here and still save my simulation or any geometries without any problem. Whereas if I start on frame 1 and then I need to add 100 frames of pre-roll, I would need to use negative frames, which are much more difficult to save in Houdini. So let's always, as a good practice, start everything in Houdini on frame 1001. And I'm going to make my simulation 150 frames, so let's set the end frame range to 1150. When I say underwater bubbles, it is tempting to create a flip simulation with additional bubbles. However, that would be quite heavy, so it's much lighter and easier to control to create a pop simulation, a simple particle system that will create our bubbles, and then we can add water later on in any editing software. So let's start by creating a geometry that will actually emit those bubbles. So let's drop down a geometry network and I'll rename it to Prep Geo. Let's dive inside, and here I want to just drop down a font node, but you can use any geometry that you like. It can be any test geometry or just a letter, so I'm just going to use letter V. And at the moment you can see it's flat, so I want to extrude it to have a nice geometry that I can use in my simulation. So let's drop down poly extrude, let's display it, and I want to increase the distance. And also now if I zoom in, you can see this geometry is still open. So on this side, we do have a polygon covering our geometry, but here it's open. So I want to scroll down and always make sure to switch on output back. Okay, and now we can adjust the width or the depth of our geometry. I will be using maybe 0.3. And now just to be safe, I want to drop down convert node. So we always want to be using polygons, and then I want to drop down normals. And as you can see in my example, I want to make the geometry create a V shape underwater and then generate bubbles from there. So let's drop down a transform node and let's just add some nice movement to our geometry. But of course you can adjust it to however you want. If you want the geometry to just drop in water, then of course keyframe it that way. But before I add any keyframes, I want to set my camera because everything will depend on that. So let's go to new camera, and then make sure to click on the padlock so that you can move that camera. And now let's just frame it nicely. Once you're done, let's just untick this padlock, and I want to rename it to render cam. Now I can go back to my geometry and start keyframing my animation. So what I want to do is for this letter to start over here in the top left corner, then go to the center bottom, then to the right, and then come back. So I will create a nice V shape with this letter. So let's alt click to create a keyframe, or right click and then go to keyframes, set keyframe. And then I want to go to the last frame because, as I said, it will kind of loop that motion. I want to go to the last frame and set a keyframe here. Then I will go to kind of the middle and I want to move my letter to the right and set a keyframe here. Then again, I will go to the middle in between these two keyframes. I'll move the V letter to the bottom and I'll do the same over here. And let's preview it. Okay, you can see it's going quite fast, and this is because we didn't set the real-time toggle. So always make sure for simulations to do that, otherwise Houdini might skip several frames and then not give you accurate results. So we always want to make sure that the real-time toggle is switched on. You can also go here to the global animation options and switch on real-time playback over here. And you can even save it as default so that you always remember it's there. And this is our very simple animation. Okay, that will do. But as you can see in my example, I also have this additional movement where the letter rotates and moves all over the place. This is just to give it a bit more interesting motion. So to do that, we'll drop down another transform node. And in here, I will use the sine function to make this letter rotate over time. So let's go to the rotate X and let's type SIN, open brackets, and then because we want to make it change over time, I will type $FF, so that stands for current frame. And the difference between $F and $FF is that $F only uses integer frames, so only these full frames, and there is nothing in between. If I use $FF, it will use the subframes as well. So even though in the timeline at the moment we cannot see that, if we go to the global settings and then we switch off integer frame values and then zoom in, now we can see that between our frames we have some subframes. So this is what $FF is reading. So it's better usually to use that. Okay, let me just switch on integer frames. Here we go. And let's close the brackets. And of course, I want to display my transform and play it. So because we have this movement, up and down movement, we cannot see it very well. So let's just bypass our first transform. So this is the up and down. And let's play it again. Okay, nothing really is happening. So let's add two more values here. So first of all, after $FF, we want to multiply it by, let's say, 5. And let's play. Okay, still nothing. So let's multiply the whole thing times 100. Here we go. So now if I change the second value to, let's say, 10, you can see that my movement is much smaller. So the angle, the maximum angle or the amplitude is much smaller. If I increase this to, let's say, 1000, you can see how big the motion is. Okay, so let's switch it back to 100. Here we go. And now let's see what the first value does. So if I change it to 1, now you can see it moves very, very slowly. So we still have the same movement, the same amplitude, but it's just moving slower. If I increase it to 100, you can see the frequency is much, much higher now. So this is how we can adjust our animation here. So the first value we can remember as frequency, the second value we can remember as amplitude. Here we go. So in my case, let's say I use 5, so I want to recreate the same settings as you saw in my render so that you can make it a starting point and then you can adjust to whatever you need. So let me copy all of this, so Control-A, Control-C, and then Tab to go to the second value, okay, so the Y value, and I will just paste it over here. And of course we want to change those values, so I'll just change it to 50, and 10, just so that we don't have exact same values in both X and Y rotation. Here we go. So it's already a bit more interesting. Let's paste the same in Z value. And again, I will edit it slightly. Let's look through my camera and go to the first frame. So on the first frame, I want this guy to face our direction. So I will just adjust these values by adding as much as I need to at the end. For example, 100 here, to just rotate this letter so that it faces us better. Okay, here we go. So let's display our first transform and let's play it to see how it looks. Okay, so you can see that this letter goes all over the place now, but we want to change one more thing. So let's bypass transform up and down. Let's go to the transform, let's name it sign. And in here, I want to make sure that whatever I do, the pivot, the center pivot stays always in the center of this letter. So what I will use is $CEX to use the center in x-axis, then $CEY and $CEZ. So $CEX, CEY, and CEZ. Now if I display the first transform again, you can see the pivot stays at the center all the time. So now we get a bit nicer animation. Okay, but now it's a bit boring. So what I will do here is actually add our sign. So it's same as here at the top, okay? I'll add the sign to each one of these axes just to give it some offset. Let's play it, let's see. So now you can see the pivot is changing, so also the letter is changing its position. So it's a bit more organic. So what I did here is I also multiplied the sign by 0.5. And I added some brackets here just so it's easier to read, but of course you don't need them here. It will be calculated correctly anyway. So let me just change these values and let's see what works the best. So let me adjust these values and I'll be back in a second. Here we go. So this is my final animation. You can also have a look at all the values that I used. So this is something we can definitely use for our sim. So let's drop down null and rename it out emitter, and let's just make sure to save our scene. So now I'll go back to the object level, and here I want to create another geometry, and this is going to be my sim bubbles. Let's dive inside, and first of all we want to object merge our emitter. So let's go to prep geo, and we called it out emitter so it's easy to find. So let's press accept. I will change transform into this object. And now let's drop down a pop network. So once we drop it down, pop network, and dive inside, we can see we already have a very simple setup over here, so we do not need to do it manually. It will also set the first frame to whatever we have in our timeline, which is great. And I can also plug in my emitter, okay, plug into the first input of the pop network, and I'll actually rename it to bubbles. Okay, let's dive inside the simulation and play. Let's see what is happening. So you can see that this letter is emitting some particles. However, the particles are not moving because we do not have any gravity in our scene. And also there's another thing that we didn't add, and that is the velocity of our emission object. So if I go back to this geometry, so to our emitter, and go to the information, so hold down control and click middle mouse button, or you can just go to the information here. You can see that we have one point attribute, which is position, and one vertex attribute, which is normal, but we do not have any velocity. So if I try to display velocities here, you can also see, let me just hide other objects, okay? You can see we do not have any velocity vectors. And it is very important that we always have velocity for all objects that we use in our simulation. And this is to make sure that our simulation is actually accurate. So it doesn't matter if we're using our object as an emitter or we're using it as a collider, we always need to remember about that velocity. And we can actually quite easily calculate this velocity. So let's drop down trail node. Here we go, trail, and let's plug it in. And by default, it will just copy our geometry for each frame and kind of create a trail for our geometry. But what we want to use is compute velocity. So result type, change it to compute velocity. And now if I display my velocities again, now you can see we have those velocity trails. And if I go to the information, I can see the point attribute velocity. I can also check the values in the geometry spreadsheet, so you can check the minimum and maximum velocity for each axis over here. Okay, that's great. So let's come back to our simulation now and let's play it again. Let's see if anything has changed. So now you can see we didn't add any forces inside our simulation. We didn't change anything here. We just added velocity to our emission object. And already the result is much different. It's much better. The particles are not staying in the same position forever. Okay, so let's start adjusting our simulation. Let's start with the pop source. So in here in the source tab, we're using the first context geometry, scatter onto surfaces. So this will stay the same. Let's go to birth, and I want to adjust the number of particles that are born each frame. So let me increase that number to, let's say, 45,000. And let's see how it looks now. Okay, so it looks better. We have more particles, but we can also see those lines that appear throughout our simulation because our emission object has those sharp lines. So to break them down a bit, I want to scroll down and change the interpolate source to back. And now if I play it again, you can see it broke those lines a bit. Cool. Now I want to reduce the life expectancy of those particles. So I only want to make them for 3 seconds. I want them to live for 3 seconds. And I also want to add some life variance. So at the moment, all particles live for exactly 3 seconds. So if I play it, you can see that after 3 seconds, all of the ones, here we go, you can see it here, all of the particles at once disappear. So I want to add some variance to it, let's say 1 second, which means the particles will live 3 seconds plus minus 1. So they can live 4 or 3.5, or they can live 2 seconds. So we'll get a bit nicer, more organic result where some particles disappear, but some still live for a bit longer. So that's great. Now we don't want the particles to go all around the place. We want them to go to be a bit tighter, so they shouldn't go far away from our emitter like that. And for this, we'll use a POPdrag. So let's drop down POPdrag and then plug it in over here. And let's play it again. And you can see that the particles move away a bit slower now. And we can, of course, adjust this value. If I put it to something lower, like 0.1, you can see that this force doesn't slow down those particles as much. But if I increase it to, let's say, 10, you'll notice that the particles barely move. Okay, so they get slowed down quite fast. So let's use the value of 3 over here. And again, you can see that all the particles have exactly the same air resistance. So air resistance set over here. So they all behave in the same way. And this is not very realistic. So what I want to do here is use Vexpressions. So let's tick this box. And then I want to add some more randomness to how they behave. So if I hover over this parameter, I can see here at the top, it says parameter and then the name of that parameter that I can use in that expression. So it's called air resist. So this is what I want to use, air resist. And let's start, for example, by multiplying it by 10. So just a simple thing to understand how it works, okay? So multiply equals, so another way to write it is air resist equals air resist times 10. Okay, so it's the same thing, but the top one is just faster. So let's use that one and let's play it. So now you can see I multiplied the air resistance times 10 by 10. If I multiply it by 0.1, now I can see it's much lower. So I take this value that I specify over here and then apply whatever I say in this expressions box. So what I want to do now is actually multiply it by some random value for each one of those points. So what I will do is type rand, which will give us a random value, and then I want to specify an attribute that I will use for that random value. So I will use the ID. Okay, so each of our points has an ID. So now I will use a random value for each point and then multiply it by the air resistance. So now we can see that some particles stay in their place, they are slowed down a lot, but some particles go very far away from our geometry. Cool, so that's much nicer, but now we do not have much control over the minimum and maximum value. So let's say we don't want these particles to go that far, and we always want some of these particles to move just a bit. We don't want them to stop straight away. So to do that, let's create another value, and I will create a float, and you can just name it whatever you want. So for example, value, and this float value will equal to our ID, okay? And now I want to multiply this air resist by that value. So now if I play it, you might have already guessed it, it's the same as multiplying our air resist directly by ID. So what I can do is, for example, type rand here. So now we'll get the same result as using rand at ID. So let's play it, let's check. Here we go, it's the same. So now what I can do here is use fit 01, which will fit all ID values between range 0 and 1 into the values that I specify. And we'll clamp all the values outside this range to the minimum and maximum of the range, which in our case is 0 and 1 because we're using fit 01. I'll make a separate tutorial specifically about the fit and fit01 functions because they are very useful expressions, but for now let's just understand that whatever attribute we use here will now have values ranging from the new minimum and the new maximum that we specify. Okay, so we want to fit our ID value, and now I can specify what I want to fit it to. So for example, 1 and 300. So the minimum value I will be multiplying the air resistance by will be 1, and the maximum value will be 300. So let's play it. Here we go. So now we can see that all the particles are moving. So the minimal air resistance that we have is 3. The maximum air resistance that we're using is 900. And now we can adjust these values however we want. So we can make it 0 to 3, for example. So now we can see they move much more. So it's just a nice way of controlling how everything behaves here. But now you can see that our particles are a bit boring. They all follow the same line. There is no noise to them. So let's drop down a POPforce. And let's plug it in here. And I'm going to use this POPforce to add some noise to our particles. So in here, if I just play it like it is, it will not change anything. And this is because in our POPforce, the amplitude is set to 0. But as I increase this value, you will see it adds a bit more variation to the position and the movement of those particles. So let me adjust it. Let's find the options that we like. Okay, that looks good. So I just want to have a bit of that noise, but again, adjust it to however you wish. And then I will scroll down and again use the expressions because again, we want to add some more variation to those particles. And I will use a very similar trick as before. So let's actually go back to POPdrag, and I want to copy all of this and paste it here. But now I want to change several things here. So first of all, a resist, we do not have a parameter like that. Instead, I want to control my amplitude. So if I hover over, I can see parameter is called AMP. So this is what I want to use here, AMP. So now each particle will get a random value, and then the amplitude will be multiplied by that value. But what I want to do here is actually use something different. So I will not use ID, I will actually use the particle age. So as the particles get older, they will get more noise. Okay, so I want to start with 0 value, and then let's say 3. So the newborn particles will not have any amplitude, any noise, but as they get older, they will spread apart a bit, so they will have a bit of noise applied. And I don't want to use a random over here, I just want to multiply the amplitude straight away by the age. Here we go. Now we can see it a bit better. So these particles here, the newborn particles, don't get as much noise as the ones that lived for a bit. Okay, but remember we are underwater and we do not have any gravity, which is fine, but we need another force that will push the particles towards the surface. And this force is called buoyancy. So in short, it's just an upward force that appears in liquids that makes objects go towards the surface of the liquid. And for that, again, we'll use a POPforce. So let's plug it in, POPforce, and I'll name it Buoyancy. Let's go to the settings, and let's make this force maybe 2 in y-axis. So now when we play it, you can see that all the particles go upwards. But again, we want it to look a bit more organic, so we do not want all the particles to go up at the same time. So we can do several things. First of all, let's go back to our POPdrag, and I will just copy all of this. Let's copy it, and I will go to my POPforce, and under the force, I will use the expression. So before we used it over here, but now we're actually using it underneath the force, and let's paste it. And now we want to check how this parameter is called. So if I hover over the force, I can see the parameters are called force X, force Y, force Z. So this is what I want to use here. So instead of a resist, I will use force.y. So this will be my force in y-axis. And now let's play it. And you can see straight away that some particles go upwards a bit faster and some stay here a bit longer. And there's one more thing I want to add, and this is some noise. So here let's scroll down, and I want to increase the amplitude, and let's see how it looks. Okay, that's not too bad, but I think I want a bit smaller swirl size. And let's maybe decrease the pulse length so that it changes a bit faster. Here we go. That's beautiful. Okay, so that's not too bad. However, if we look at our references, we can see that bubbles underwater behave very similar to the actual water. So some of the bubbles some of those particles should stick together. We should have some nice breakups, some nice gaps in between those particles. But at the moment, all particles don't seem to have any forces keeping them together or pushing them away from each other. And to fake this effect inside POPs, we can actually use a POPfluid node, which again is a node that was introduced in Houdini version 17, and it's been very helpful since. So let's just plug it in and let's see what it does straight away. So now you can see it changed the look of our simulation a lot. But if I zoom in, you can see that some particles created groups and some particles were pushed away from those groups of particles. So even though it doesn't look like water, you can see that it does something. It definitely works. And what I want to do here is actually not experiment on our simulation here. I want to make another simulation that will be much simpler so that we can actually see how everything works. So let's drop down a sphere, and let's drop down another POP network. Okay, let's dive inside, and here I want to add some gravity. Here we go. So we have those particles falling, and now let's add the POPfluid node. Okay, and let's play it. So now if I play it, you can see it much better. So again, we have those groups of particles. So some particles are pushed towards their neighbor particles, but some particles are actually pushed away. So we get those nice fluid-like patterns. And we can adjust the particle separation to adjust the distance between those particles. So if I set it to higher values, you will see that the particles tend to spread more because they want to be further away from each other. But if I decrease that value and play it again, you will see that the particles are very tight and they create smaller, tighter groups because now they can be closer to each other. Now we have the constraint iterations and constraint stiffness. So these two settings help us determine how closely this particle separation is matched. So let me just increase it a bit so it's faster. So now we'll really try to make this particle separation equal to 0.1, whereas if I decrease that value, it will be matched a bit loosely. So you will see some chunks of particles, some separated particles, and so on. And the constraint stiffness does a very similar thing over here. So it just gives us a bit more control. And I will not go through all the settings today. I believe it's a topic for a different tutorial, but just a few more that we will be using. So tensile strength. Again, if I play the default one, you can see that the particles do not spread that much. If I increase the tensile strength, you can see that the particles push away from each other and there is more space in between them, and they also occupy bigger space. And viscosity mimics the same effect as in flip fluids, so it will make our fluid appear more sticky, more viscous. So if I increase this value, you can now see, maybe just change the tensile strength to the default. So now you can see we get this blobby effect. So almost as we're pouring honey, whereas if I decrease it, you can see it's more like water. And then one more thing is the neighbors. In short, the neighbor settings adjust how many nearby particles affect each other. So you can adjust the size of that neighborhood and also how many points are in each neighborhood. So if you're not sure about any of those settings, it's a good idea to stop here and maybe adjust some of those and see how it affects our simple simulation. So what I usually do is just change this value to almost the minimum and almost the maximum, and then run those two simulations and see how they compare. It's the easiest way to really understand what all of those settings do. But let's go back to our main bubbles. Okay, and in here, let's play it just to remember how it actually looks. Okay, so this is not good. We need to first of all reduce the particle separation. So let's reduce it to maybe 0.03. Let's play it. Okay, this is much better. And we can already see that some particles stick together, and we also have some droplets or smaller bubbles that are a bit further away. So this already gives us a bit nicer look, a bit more fluid-like look, so it looks more organic. I will also increase the constraint iterations to about 60. And I want to increase the constraint stiffness, let's say 300, and let's check now. So I want those bubbles to really keep together. I want them to stick together and create those groups of particles that will look like bubbles and then will spread apart. Okay, so now you can see we have these chunks of particles, and as they get older, they should spread apart. Okay, that's great. So I do not want to create a full fluid simulation or something that looks like liquid. I actually want to create bubbles. So I can adjust these settings a bit more. Let's reduce the tensile strength, but also increase viscosity. So again, I want these bubbles to really stick together. And I will go to the neighbors as well, and increase the maximum neighbors just to create a bit bigger chunks of particles. And let's run a flipbook and see how it looks. Here we go. So this is our simulation so far, and you can see that we have some particles that stick together. Some of them are separated, so we have those smaller bubbles created here, and after some time they pop, they disappear. Also, we have some nice noise, and we have some variation in their life, in the noise, and also in how far away from the center of this movement they actually go away. So now if we want to change anything, we can go back to our simulation and adjust the settings. So most of the settings will be under the POPfluid. So this will control the fluid-like behavior of the particles. We can also adjust the buoyancy. So we can adjust this value over here. So how fast the particles actually go up. And then remember that we added some noise in this POPforce and also in our buoyancy. So here at the bottom, I'm using the amplitude of 3, but if I want to have more or less noise, I can adjust these values as well. And finally, there is one more thing that we didn't look at, and this is in the pop source under attributes. You have the inherit velocity option. So remember, we added velocity to our emitter, and this is where we can adjust how much of that velocity we want to use. So you can multiply this velocity over here. And there's one more thing that we forgot about, and this is the collision. So our geometry, our emitter, should also be a collider so that nothing penetrates this geometry over here. So let's use this guy and drop down collision source. And we have two outputs, so let's drop down null, and this one will be out geo. Let's duplicate it. And this one will be out VDB. So you can see that the geometry, if I just zoom in, this is just our geometry. If I go to the settings, I can see I have my velocity here. It's very important. If I go to the VDB, after a while, you will see a VDB representation of our geometry. And you can see it's not very accurate. So if I go to the collision source and volume tab, here I can adjust the voxel size. So the smaller the voxel size, the more accurate our collision will be, but also it's going to be a bit slower. So let's maybe change it to 0.08, and this looks fine. Okay, so now I want to go inside the POP network. I want to drop down a static object. And here, first of all, I want my subpath. So this will be, if I go here, this is the geometry that I want to use. So here in the subpath, let's just click on this icon over here and find our out geometry. Let's hit accept. Then we don't need to use these settings, but we do need to use deforming geometry because our geometry is moving. So let's make sure this is ticked as well. Let's scroll down and go to the collisions tab. And over here, if I scroll down a bit more, I want to change the mode. So in most cases, you will use the volume sample. It's the quickest one, and also with the collision source, you get the VDB representation of your geometry. So if you scroll down, you can plug in this VDB representation under the proxy volume. So let's find it, out VDB. Okay. And let's merge it so that we can actually preview it in our simulation. So make sure in the merge node, first input is always your geometry, your collider. The second input is the simulation, and then we plug it in like so. So now if I go to the static object again and display the collision guide, you can see our VDBs over here. So they are not very accurate. So let's go back here again, and actually I will reduce it a bit more. And if I go back, you can see it's adjusted straight away. So I can either display the geometry or I can display the VDB representation. Brilliant. So now our simulation is done. So we have our collisions, the look is completed. So now we want to render it out. And before we render it, we need to make sure that our particles are meshed. So the same as we would do for a flip simulation. And let's just simulate a few frames. So you can cache the simulation out if you want to, but I'll just go to maybe 10, 14 or 15 sounds good. Okay, let's zoom in so that I can see the particles a bit better. And now I want to drop down blast node. So you can see that by default, I get the particles and also my collision geometry, but I only want to mesh the particles. So let's drop down blast, and then from drop down menu, I want to use the stream source first input. So this is our particles, and I want to delete non-selected. So now I get just the particles without our geometry. And next, similar to any flip, I want to use the particle fluid surface node. So let's drop it down, particle fluid surface, and let's plug it in, display, and now you can see the mesh of our particles. But of course, it's not very detailed, so we need to adjust some settings. And again, I will not go into too much detail about this node because it's a topic for another long tutorial, but we'll have a look at the most important settings. So first of all, the particle separation. And we want to link it to whatever we used inside our simulation in the POPfluid. So let's find POPfluid, go to parameters, particle separation, right click, and then we want to copy parameter. And then let's go inside particle fluid surface, right click, and paste relative reference. So now whatever we use in our simulation will also be used here. So you can see straight away it's much better. It's also slower because we're using high resolution. Next, let's adjust the droplet scale so that we can see these particles separated a bit more. So now we can see some of the particles create those little droplets. And I will also want to decrease the influence scale. So once I decrease it, you will see that the particles break apart a bit more. But now you can see all of those sharp edges, and this is because the resolution of our mesh is quite low. So in order to increase that, we need to decrease the voxel size. So the more voxels we have, the higher resolution we'll get. So let's decrease it quite significantly. However, if your workstation is not very strong, you want to just decrease it slightly and then check how it looks, and then decrease it slightly again, check how it looks, and then find the value that is the best. But I know I can handle 0.3, and you can see it's calculating, it's taking a while, and now you can see those nice rounded particles, rounded mesh that we have over here. So now what I would do with these settings is go and pick several frames. So I would go back to my flipbook and choose the frames where I can see different stages of my simulation and then test it on these frames. So I do not want to scrap the timeline, I just want to pick 3 or 2 frames and test it there. And once I'm happy with the look of my mesh, I can just drop down null, and the next stage would be rendering. So this is out mesh. And this is everything that we need for rendering. Let's make sure that we're displaying the last node, the one that we want to render, and then let's go back to the object level, select this geometry, so I can switch off prep geo, just select the sim bubbles, and then go to render, sampling, and make sure you're using the velocity blur. Otherwise, the velocity blur in your mantra will not show up. So we've got the camera, we've got the geometry we want to render. Let's add some materials. So I'll go to the material palette, and I will actually use a very simple water shader. Here we go. So I want to use the basic liquid. Let's just drag it in. If you want to adjust some settings, feel free to do that, but I will just use the default. And in here, in my sim bubbles, I want to go to render, material, and now I will link my basic liquid over here. Next, let's set up some lights. So I want to drop down environment light. You can use the shelf tools. So let's hold down Control, click on environment light. And now let's pick one of the environment lights that are available in Houdini. So I will use the Lenong, and let's click accept. And I will also rotate this light. So minus 180. So now it's actually the opposite of what we usually have, and this is again to give this nice feeling of being underwater and having the bubbles reversed. And just to add a bit more light variation, I will drop down a distant light, and then I will look through that light, so look through distant light, and then click on the padlock, and then I will just put it at the back, so just to make a very subtle fill light over here. So let's untick the padlock. And now I want to adjust the color a bit, so I want it to be a bit more blue, very light blue, just to give a bit of a variation again, to make it more natural, more organic. Here we go, and let's decrease the intensity. Here we go, so let's go to the out level and we can set up our mantra. So let's drop down a mantra node, just simple mantra. Let's just render current frame, so usually you want to render frame range, but now we're testing, so one frame is fine. Let's make sure we pick our camera, so render camera. If you want to make very fast test renders, you can override camera resolution and only render half resolution or even quarter resolution, it's fine. But yeah, let's actually do half resolution to make it faster. And then let's go straight to the rendering options. In the output picture, you would choose where you want to save your file, but for now we're just rendering to Mplay, so let's go to rendering, and I want to change the rendering engine to physically based rendering, and I also want to allow motion blur. I will leave the rest of the settings as they are for now, but what you will find is that motion blur can be quite pixelated. In that case, you want to increase your pixel samples to, for example, 6. Don't go too high because this will increase your render times significantly. So these settings are fine for now, and what I want to do is just render to Mplay. So again, single frame, render to Mplay, and I'll be back once it's done. So here I have this half-res render of frame 1015, and I also made another render which is full resolution of frame 1027. So now I can take those renders, I can take my flipbook, compare it to the references, make all the adjustments, and then render the final sequence. However, before I actually render everything, I want to make sure I cache my mesh because it can be very heavy. And before the render actually starts, it first needs to calculate the simulation and then calculate the mesh for each frame. So in order to make it much faster, we would just drop down a file cache node just before our out mesh, cache it to the disk, and then make sure load from disk is switched on before you actually start rendering. And that's it, guys. Here's the Houdini underwater bubble setup from start to finish, from prep to rendering. I hope you enjoyed it, and if you have any questions, feel free to ask them in the comment section, and I'll see you in the next one.